In our next section, we will review exercises from Chapter 17, where we explore some of these ideas about finding the expected value, finding the standard error, and using the normal curve to help us make predictions about the likelihood of various outcomes. There we go. In our first item, we have 100 draws made at random with replacement from this box 1, 6, 7, 9, 9, 10. So the first couple questions are pretty easy. How small can the sum of draws be? Well, the sum of draws depends on the, there we go. The sum of draws depends on the number of trials. So we have 100 draws. And if each of our 100, and we're looking at the outer edges of our sum, the range of what the sums could be. So in this case, the smallest could be 100 draws times the smallest value, 1. If we got 1 on each of our draws, then the smallest the sum could be is 100. How large could it be? Well, again, we have still 100 draws. Remember, they're with replacement. And now we need to look at the highest value in the box. That's 10. So 100 draws times 10 leads us to 1,000 as the highest value that our box can, the sum can represent. Now it's a little trickier to do part B, because we now need to know the chance of the sum being between 650 and 750. In order to find this, we can start out thinking about this conceptually, but ultimately we're going to want to do some calculations to solve this problem. But we know that 1% and 99% are probably not going to be the answer. How do we know that? Because remember that in our earlier problem, how 99% of the scores were within a very small portion of the range, right? 99% were within 50 to 100, and that left a lot of space here on the edges of the distribution. And so we're revisiting that idea now. And we can see that 1%, 99%, those would be way out here. And if this sum is between 650 and 750, that's somewhere in the middle range of the distribution. How do I know that? Right now, I'm just using logic. If I know that the edges are 100 and 1,000, then the middle has got to be somewhere, you know, in the middle. And since this box is a 1, 6, 7, 9, 9, I know it's probably around these scores. But again, we're going to do some math here. It's just helpful to think about this conceptually. Why? Why not just jump in and do the math? Well, because sometimes you do the math and you make a mistake, but you only see that mistake if you're already prepared to think about these problems conceptually and logically. Like say you made a mathematics error and you said the chance was about, you came up with 99%. Well, logic would tell you that's probably not it. And I do see errors like this all the time on exams and other places. So it's always good to be thinking, does my answer make sense? So here we have the sum between 650 and 750. So what values do we need to solve this problem? Well, just like before, we need to know the average of the box and the standard deviation of the box, and then we can get our standard error. What's the average of this box? Let me see. The average is 7. Thank you, Stephanie. You win a cat, but you can't have the standard error. She's a real sweetheart. I mean, they're all sweet, but I'm probably going to keep her. She's adorable. The standard deviation, why not have 4? That's even a better number of cats. But seriously, people, if you know someone who needs a kitten, these are great kittens. Remember, I'm just fostering them so they don't end up in a shelter and live in a cage in the beginning of their lives. So, you know, don't be afraid to let me know you have a friend who needs a cat or something. So back to the matter at hand, we know the mean is 7. The standard deviation is going to be 3. We just walked through finding the standard deviation. So I'm going to just give you the standard deviation in this case, rather than walking through finding it again, since we just went through this a few minutes ago. And now with this in mind, we know that the expected value of the box is going to be equal to, oops, or I should put here sum. It doesn't, my subscript doesn't really matter. I just like to be very precise. So we're getting the expected value of the sum. And the expected value of the sum is, remember, the number of draws times the average. So that'll be 100 draws times 7 for 700. Come on. Yeah, come on. So our expected value is 700. We know that's going to be the average here. And note that I'm going to draw a second line below my distribution for my standard units, which I'm just going to write in SU, standard units, because I'm running out of space. I'm trying to write bigger tonight because I've heard some people are having a hard time reading the things in the video. So give me some feedback if it's still too small, but I'm doing the best I can here with our space. So the expected value of the box, and we're looking for the sum being between 650 and 750, which would be about here. Here's 750 and 650, and you can see how this resembles really very much the problem we already did. We know that the standard units for 700 are going to be 0. That's at the mean. We can convert 650 and 750 to z-scores, and let's go ahead and do that. I'm going to minimize some of this information we've already done. to give us a little more space. So remember, when we want to convert 600 and 700 to z-scores, we can use our z formula for multiple draws. So 650 minus 700 over the standard error, which I guess we didn't get yet, but it'll be very easy to get. Because remember, our standard error is just the square root of number of draws times the standard deviation. And we know our standard deviation is 3. The number of draws is 100, so it's equal to the square root of 100 times 3. Oops, I'm getting ahead of myself. Square root of 100 is 10, times 3 is 30. So the z-score for 650 is negative 1.67. And if we find the z-score for 750, you should already be able to tell that it's going to be a positive 1.67. How can you tell? Well, because this 650 is 50 units away from the expected value, and 750 is 50 units away from the expected value. So they both are the same distance from the expected value. And since this is a symmetrical distribution, we know it's just going to be the same score, but not negative. Does that make sense? So this is not. Okay, so just like this is as always for this process, we need to find the proportion of the distribution that lies within this area. Imagine these are aligned correctly. And so the mean to z for 1.67, the area here, is about 45%. You can find this in column B of the table, the z table. And it's going to be 45% over here too, which means that the sum probability for the percent chance of a score that's in this anywhere in this shaded region is going to be 45 times 2, or 90%. So 90% is our answer. Any questions about how I got that? This idea, finding the chance of a score range, is a type of problem you'll definitely see again. And we will practice it again too. I'm just mentioning it to help you filter through what's, the most important types of problems to pay attention to. So now we can match these standard deviations, match the lists with the standard deviations. How do we do this? We can use their shortcut for finding the standard deviation, which was big number minus the small number times the square root, was it? This shortcut is helpful for you, but not one I find myself using much. Because when you do big data, it's all computational nowadays. So we have big minus small, and then they give us this fraction with the big number and the fraction with the small number. And what those mean are the fractional number of tickets that have the big number and the fractional number of tickets that have the small number, which is an important distinction. And I'm just representing it like this for ease of representation here quickly. So big minus small, let's look at A here. What's our big number? It's 1. The small number is -2. 1 minus -2 is like a plus minus a negative. So it's 3 times then the square root of the proportion of tickets with our big number. Well, we have 3 tickets here, and our big number is only on one of them. So that's 1/3 times our small numbers on 2/3 of the tickets. So we can see that this A is number 3. We can repeat the process for each of these. We'll do another one. For item B here, we've got 16 as our big number. Minus the small number is 15 times the square root of the proportional representation of the numbers. So the big one is, again, 1/3, and the small one is 2/3 of the tickets. And we can see 16 minus 15 is going to be 1. So B must be I. Any questions about this? Does what I'm doing make a lot of sense to everybody, or do we need to keep doing these? Well, let's do one more. And but this is a pretty easy idea. I mean, this simplification is helpful. And although I don't use it much in my big data analyses, because there are thousands of cases, you could use simplifications like this, again, when you're in your, like in a clinical context, where you might have a smaller number of cases, but also where you often do have dichotomous outcomes, or just two, where you just have 2 values. Usually a 1 or a 0, because you've recoded things to be like a 1 or a 0, or there's a lot of yes/no outcomes. Another example of an outcome is does a person come back for a follow-up visit? Yes, no. There's tons of examples of this. It's a whole big field of statistics that's used all over in health sciences, these scenarios that have dichotomous outcomes. So, this definitely has some utility here in the, terms of long-term applications you might make of this. We again have a situation 1 minus a -1 is going to be 2, right? And then our proportional representation, now we have 4 possible tickets or 4 possible outcomes in the box. And our big number is on 1 of them and the small number is on 3 of them. So we can see now that this has got to be V or 5, right? All right, I'll leave you to do the last couple. I think this is pretty simple process, and we can save our time for something more complicated, like hopefully chapter 18. So a die will be thrown with some number of times, we don't know, and the object is to guess the total number of spots. There's a $1 penalty for each spot that the guess is off. For instance, if you guess 200 and the total is 215, you lose $15. It's an absolute loss based on the absolute difference between your guess and the total. So would it be better to choose 50 throws or 100 throws? Exactly, it's 50 in this case, because as you, this is hitting home the idea that the absolute error goes up for the increased number of trials, and in this scenario, the penalty is based on absolute error, not the standard error. "100 draws are made at random with replacement from this box that's like a die, excuse me. If the sum of draws is 321, what is their average?" Well, how did we get the sum of the draws? Oops. If the sum of draws is 321, that occurred across 100 draws. So we can take our 321 and divide it by the 100 draws and get an average of 3.21. To go the other way, if the average of the draws is 3.78, what's the sum? Well, you can see where this is going. If the average is 3.78, we're going to multiply by the number of draws, and there's 100 draws. So this is equal to 378. And now we want to estimate the chance that the average of the draws is between 3 and 4. So when we are estimating the chance that the average of the draws is between 3 and 4, we can assume that we have that the average of the draws will be between 3 and 4 when the sum is between 300 and 400. Thus, the expected value of the sum is 350. Where did I get 350? Well, if the average of the draws is between 3 and 4, then the sum of the draws would be from 300 to 400, which I got using the same process we did up here. And the expected value of this range would be 350. So the next thing we need to know to finish out this problem is in addition to the expected value, is of course the standard error, because the standard error and the expected value always go together. And the standard error is going to be equal to the square root of the number of draws times the standard deviation. Could we find the standard deviation? Yes, of course, we can get the standard deviation of this box. I'm going to just give it to you right now because we just did the standard deviation. And the standard deviation is 1.7. So then our standard error is equal to the square root of 100 draws times 1.7. So it'll be 17. Why am I always noting the standard error with the subscript sum? I'm doing that for a reason, because this is the standard error for the sum, and we're going to encounter other standard errors as we move through the rest of our material. We're going to have a number of we're going to have multiple standard errors. So it's good to get in the habit of taking note of which standard error formula you're using, which seems simple now since we only have the one, but trust me, once we have many, it's trickier. So now that we have the standard error, we can easily estimate the chance of the average of draws between 3 and 4, because we can use the same process we did earlier. We can get the standard error, we can use our standard error to convert 300 and 400 to standard units and get the percentage of the curve that lies between those units. So sorry, I feel like everything's a little bit off because I'm trying to write bigger and the space is not working out as I'd hoped. I have a new strategy for this that we'll use on the next problem we encounter like this, but we'll just keep moving forward on this one. 300 minus 350 is going to give us a negative 50 over 17, or a standard score of -2.9. So if this 300 was -2.9, and 400 is going to be a +2.9 by the same process that we looked at earlier. It's off by the same amount from the mean. And we can just find the mean to z proportion for 2.9, and you'll see it's a very high proportion, like 49.6. I don't have my z table right in front of me, but I know the total is going to be 99.7. Thank you, 49.8. So 49.8 over here, 49.8 over there, for a sum total in this region there's a 99.7% chance that the average of the draws is between 3 and 4. It's okay if you have 99.62, I have 99.7. It's not a significant difference. I, like on an exam, I would give credit for a range that included both. It's a matter of rounding error at certain points. Any questions about the process though? Okay. A gambler plays roulette 1,000 times. There are two possibilities: betting $1 on a column each time, or betting $1 on a number each time. Now, to get this, we have to remember that the column that, there we go, that a column pays 2 to 1, and there are 12 chances in 38 to win. A number pays 35 to 1, and there's a 1 in 38 chance to win. Okay, so I thought something was missing. So we are missing, sorry, I obviously didn't copy over the second piece of this item, as I just didn't see it. I solved these, like you, I solved these in my book, and then I just copy over this material for our slides. Sorry about that. I obviously do a ton of copying and pasting. So we can evaluate A, B, and C. Each is a true-false scenario. And let's look at what happens if we play each one. And I'm not ignoring your question, Stephen, but we really have to get to some of the later material today. And what's going to be really important and trickier to do going forward are the next things that are coming. So let's just think through this problem kind of quickly, but I'm not going to give you a bunch of like roulette problems on your next exam. So, although it would be fun, of course, at least studying for it would be fun. We need to think through first what happens if you play each of these possibilities. There we go. We bet $1 on the column. Well, if you bet $1 on the column, that's like pays 2 to 1. We're not really, let's think first about the chances of winning. So there's 12 chances in 38 to win. Whereas when you bet on a number, there's only 1 chance in 38 to win. And when you bet column, you bet on the column. What that means when the pay to it pays out, it means if you put in $1, it's going to pay 2 to 1. So it's going to give you out 2 for each one you put in. I did just say, Stephen, that the roulette there will not be a bunch of roulette problems on the exam. Will there be maybe one? Maybe. Probably. I mean, I'm not really worried about it. I almost just said, let's skip this item. So that's why I'm just trying to walk through this quickly and not set up a bunch of more boxes. I really want to get to our later problems. So the average of the box. So we have, if you play one, the net gain is like the sum of 1,000 draws from a box with 12 tickets marked $2 and 26 marked $1. So because we're playing roulette 1,000 times. So one, this is like a box where we have $2 times 12 tickets. And 26 marked -1. Right? So that would be the box for item 1. The average of the box is -2 out of 38, and the standard deviation is about, let's see, it says $1.39. Sorry. And we can go through and find the expected value, but just trust me, since we already did this several times, the expected value here for the net gain is a -$53. And the standard error is $44. If you play 2, so let's just, now that we've got all the numbers for this one, let's just think through the comparison for 2. On 2, you bet $1 on a number each time. So there's another box with a bigger standard deviation. The net gain has the same expected value, but the standard error will be, for the second box, $182. So, and it's not surprising that the standard error is so much bigger here because the standard deviation is much bigger. Chance variability helps you overcome the negative expected value. So you're more likely to come out ahead when you, with B. The chance variability also makes it more likely that you'll lose big. So we can look at these here and see that the chance of coming out ahead is not the same with 1 and 2. Obviously, it's not. The chance of winning more than $100 is bigger with 2. Well, sure, of course it is, because 2 pays 35 to 1. So we really don't even need to know these other statistics to figure that one out. The chance of losing more than $100 is bigger with 2. Of course it is, too, because this is just gambling 101 here. If it pays out big, then you have a better chance of losing big too. And we can see that illustrated, B and C here. We can see why these are true when, if we compare the standard errors of these two scenarios. No, you don't lose at this. If you bet $1 each time, don't you lose at the same rate? No, because you bet a number pays 35 to 1, but there's a 1 in 38 chance to win. So you don't lose at the same rate. This is why the house always wins. The odds are set up so that the house has a better chance of winning. And I would love to spend a lot more time on probability. It's one of my favorite labs to do. a gambling lab. We're just not, we don't have time in the spring semester, given that there are certain labs that we have to do, you know, per our curriculum. And learning to gamble, unfortunately, isn't one of them. So we have this 2 problems left in this chapter. 100 draws are made at random with replacement from the box, -2, -1, 0, 1, 3. How's this going to work out? The sum of the positive numbers, and so we need our expected value and our standard error. And we're not just looking at these from this box, we are looking at these numbers as positive numbers or negative numbers. So, or the sum of the positive numbers. So the sum of the positive numbers we can visualize this idea more easily if we recode the tickets in our box. Like, let's recode our box to a 0, 0, 0, because you can see -2, -1, and 0. None of those are going to count in our mathematics here. But 1 and 3 are positive numbers, so they do count. So thus, the average of the box is, we can get by, it's going to be 4 divided by 5, because there's 5 total outcomes, and the sum of 1 plus 3 is 4. Obviously, the zeros don't affect us, the sum there, and that's equal to 0.8. And the standard deviation is 1.2. So what will the sum be about? The sum across 100 draws? So we've got 100 draws times an average of 0.8. It's 80. Give or take a standard error of about 12 or so. How do I know it's 12? Well, just because, remember, the standard error equals the square root of draws times the SD. So we got the square root of 100 times 1.2, 12. So 80, give or take 12. Give or take, of course, being layman terms for plus or minus 1 standard error. And I think we should, let's just skip 13 so we have a little bit of time at least to talk about the next chapter for now. I don't think we need to do another box problem. Unless there's a big objection. We'll focus on some of the standard approximation, the normal approximation computations in our next unit. And we'll be doing less with the box models as we move on. Remember, for the most efficient way, do some statistics every day.